Video 16 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is second derivatives of the energy. In this short lecture, we want to look at second derivatives of the energy in the presence of an external electromagnetic field with respect to two components, F alpha and F beta of the field. Now, we learned a few lectures before that the Hellman-Fermi theorem tells us that the first derivative of the energy in the presence of the field with respect to a component of the field is actually the same as the expectation value of the corresponding derivative of the Hamiltonian. And we're going to use that, which means in order to calculate the second derivative of the energy, we now have to take just the first derivative of this expectation value of the derivative of the Hamiltonian. Again, here the derivative is with respect to a different variable. It's the external component of the external field. Then the integration, which is of course over all positions of the electrons, and therefore we can interchange differentiation and integration. And underneath the integral, we have again a product of three terms. The complex conjugate wave function, the derivative of the Hamiltonian with respect to the component alpha of the field, and again the wave function. So we have to use the product rule and get three terms. One where we take the derivative of the wave function in the bra, meaning the complex conjugate wave function. Then we take the derivative of the wave function in the ket here. And finally, we take the derivative of the operator, which is the derivative of the Hamiltonian with respect to the alpha component of the field. So we get a second derivative of the Hamiltonian, one with respect to the alpha component of the field and one with respect to the beta component of the field. If you now insert these derivatives of the Hamiltonian, and the first derivative is where we get now the interaction operator, the part of the perturbation operator, which depends only on coordinates or canonical momentum or spin operator of the electrons, and here the alpha component. And then from the part of the Hamiltonian, which was quadratic in the field, coming from the a squared term, the term where we had the vector potential squared. Taking the first derivative, we still of course have one field component. Whereas taking now the second derivative, which means the derivative of this expression again, we only have these two operators which come from the vector potential squared, which come from the second order Hamiltonian. Inserting these first and second derivatives of the Hamiltonian in our expression up there, and then evaluating the second derivative at zero field strength, which then of course means that here in the part where we had the first derivative of the Hamiltonian here and there, all the parts which still depend on the field vanish because we set the field equal to zero. So here we only have this first order operators, and here in the expectation value of the second derivative of the Hamiltonian, now we don't have the field-dependent perturbed wave function anymore, but just the unperturbed wave function because we evaluate at zero field strength. Later on, in some later chapters, we are going to come back to these expressions here if we want to derive second derivatives. So we need an expectation value of the terms which are the second derivatives of the Hamiltonian. And then we have two integrals where we have a first derivative of the Hamiltonian and the derivative of the first derivative of the wave function, either in the bra here or in the ket. I want to finish this chapter by anyway using our perturbation theory. So expressing this perturbed wave function through perturbation theory. And if we do that meaning this expansion in a zeroth order wave function, a first order correction to the wave function second order, and so forth. Well, the first order correction to the wave function, of course, is linear in the field, the second order is quadratic in the field. Now, taking these derivatives again and evaluating at zero field strength, then means that here we will get the first order correction, we get the derivative of the first order correction to the wave function with respect to that field component here in the ket, which is this term, and here in the bra, which is this term, and that term, of course, stays as it was. Now, of course, I could insert our expression for the first order correction to the wave function, which is that we expand it in a basis, and as basis in perturbation theory, we normally use the complete set of unperturbed wave functions. Doing that would bring us back to the expression for the second order energy correction, as we had it in the last section about perturbation theory.